All right, thank you. As you say, performance of retrofitted reinforced concrete bridge columns in Cascadia Subduction Zone earthquakes. A lot of people have been involved with this, so I wanted to make sure I had everybody's name on there. Several grad students. This is a project that we've been working on for probably 3-4 years at this point, and we actually have some more work kind of going on here as well to look at the behavior of the footings and retrofitting the footings. So an overview of the items that I'm going to talk about today, give you motivation for doing the study, and then talk about the different phases of the project that we've been working on. So the motivation here is that there's a lot of bridge columns in service that are seismically deficient. Columns that were built back in the 1950s, 1960s, that were not designed for, either not designed for seismic forces, or if they were, not designed for forces at the level that we use today to design for earthquakes. And so there's a particular concern here in the Pacific Northwest. If you look at the graphs I'm showing here, these are actually some test results from research at UC San Diego in the 90s. So this problem isn't new. And the technique has been developed to put jackets around the column to retrofit them. Gives the concrete confinement, provides ductility. You see there, significant difference in performance. The column is able to yield in flexure and exhibit a lot of ductility once you put that jacket around the column. So this is nothing new. This has been around for a long time. The technique has been used. And up where I live in the state of Washington, WashDOT has been doing this out in the field. And they started doing this right about the time that this study took place, 1991. So they've been doing this for over 30 years now. But they have a concern that when you look back at this old research, and you look at, in particular, the testing protocols that were used here, the tests that were done were more suitable to strike-slip earthquakes, the type of earthquakes that we have in California. Not necessarily the subduction zone earthquakes that we could have in the Pacific Northwest, which have the potential to be large magnitude, but also very long duration earthquakes. So there's a concern here about duration and fatigue, which is what kind of led us into revisiting the concept of using steel jackets and maybe some other types of jackets to retrofit columns, and actually looking at what kind of performance we would get in Cascadia Subduction Zone earthquakes. So I'm going to jump right into an experimental study, which was kind of the first big piece of the puzzle that we started working on. So you see there are 6 columns that we tested, and these were about 1/2 scale, or maybe a little less than that, about 40% scale. We took a look at, WashDOT gave us access to their some of their data, which was very nice, and so we were able to do some inventory categorization on kind of what's out there in the field, at least in the state of Washington. And we used that to help us select the parameters in our columns. So we varied the quantity of reinforcement, we varied the axial load on the column, we looked at changing the shear span on the column, which was the height to depth ratio. And we actually varied a little bit as well the loading protocol that these were tested under. So we did a set of columns with steel jackets around them, and I'll show them in a little bit so you get a kind of a picture of what it looks like. We did a set of 6 that were retrofitted with steel jackets, and we did another set of 6 that were retrofitted with carbon fiber jackets, which is actually not a technique that is being used in the field that often, at least not in the state of Washington. But we wanted to start to look at this as a potential alternative. The cost of carbon fiber has come down over the last 30 years, and so this is something that WashDOT's getting, interested in using, and maybe potentially kind of switching from their standard steel jackets over to carbon fiber jackets. I just wanted to show you the rebar in the columns. There is some transverse reinforcement. So most of what we looked at, there is some level of transverse reinforcement, but it is nowhere near what we would have in columns designed to our modern codes. A look at the footings. The footings that we used in this study were detailed so that they wouldn't fail. So there's a lot of rebar in the footings. This is actually not reflective of typical practice in the state of Washington. Most of the footings have a lot less rebar than this. So there may be some concerns with the footings as well, and that's something we're going to be looking at in a future phase of the research. So the intent here was to isolate column behavior and not look at the potential for failure in weak footings. So I just wanted to kind of quickly go through, give you a visual on what these things look like as we're building them. And when we did the steel jackets, there's showing the steel jackets that we put on. We actually had them prefabricated. But when this is done out in the field, you typically have two semicircles, and you have to seam weld the two semicircles. So we cheated a little bit and had the whole thing kind of prefabbed and dropped it over the top of the column. But this is what they look like. So you're putting, in the field, this would be an existing column. You're putting that steel jacket around the column. And normally they leave a little space in there that gets filled with a concrete grout. So it gives you nice, good contact over the full surface. So there's what they look like. If you look closely, there's some nozzles on the columns where we attached to pump the grout into the columns. You may have, I'll back up a couple slides, you may have noticed some holes in the column, and that was actually for instrumentation. We put a lot of instrumentation, LVDTs, on our test specimens, so we put some holes in there to be able to run those rods through without having the instrumentation rods come into contact with the steel jacket. Here's a look at one of the fiber reinforced columns. You see the FRP wrapping down there. For these, we actually didn't extend the fiber the full height of the column. When we did the steel jackets, we did extend the full height of the column just because that's what WashDOT typically does. But if you have a flexure-controlled hinge, you can get away with only confining that lower hinge zone and potentially not having to put the steel jacket over the entire column. You have to make sure it doesn't fail in shear either. For reinforcement, we worked with Nucor, and they actually made us kind of some special batches of grade 40 reinforcement in a little bit larger bar sizes, because grade 40 is the prevalent reinforcement that we had in these columns back in the 50s and the 60s. So these days we're typically using grade 60 or above, but we wanted to try to simulate that grade 40 behavior. But there'll be a little bit more to come about the reinforcement. So here's the test setup. We tested the columns as cantilevers anchored down to the strung floor in our lab, lateral actuator to apply the load, and we also applied gravity load on the columns. And there's a photo of it. And if you kind of look at the top, up at the top of the image there, we had a roller set up so that when the gravity load is applied, it was able to translate along the top of the column. It let us kind of better maintain that P delta effect on the test column. There's a photo of what it looks like, little detail showing you a little bit more about what was going on up at the top there. So I mentioned early on that the big motivation for wanting to do this study was looking at a more specific type of earthquake here, actually looking at a long duration earthquake, more characteristic of the Cascadia Subduction Zone. So this was our loading protocol. This has more cycles than typical protocols that are used for earthquake testing, and we developed this protocol. So I'll touch on that a little later when I get into some of the modeling that we did. So there's a look showing you on the x-axis there the number of cycles, cumulative demand from the loading protocol. So it's a more demanding protocol than what has typically been used in the past or what was used when they did those tests, roughly 30 years ago at UC San Diego. We also had a test in there where we included a specific earthquake response. We input that on the column as a loading protocol. So we did a standard reverse cyclic loading protocol, which is pretty typical for a lot of earthquake testing. And we did another one that was where we took one of the results from our analysis and we imparted that motion onto the column, and that's what you see here. That didn't actually fail the column, so we then followed it up with an aftershock motion. So I have a little video here. Let me see if I can get this to play. Do I have to click anything to make it? We'll run this. So this is just showing, I wanted to show, we sped it up, of course. Normally when we do these tests, we run a cycle, we stop, we mark cracks. So it's a long test, but we're speeding it up here. Just kind of taking you through the whole test. And the damage that you see is typical of what we saw in these columns. We had 12 of these tests, so this is just one example, but you see a lot of action down at the base of the column. You're getting plasticity at the base of the column. And we did see some concrete in the footing kind of break and spall, but for the most part, the jacket did an excellent job of confining the concrete and giving us that nice ductile response that we wanted. So here's an example of a hysteretic loop from one of the column tests. And one of the things, you see the little numbers there, one of the things that we were keeping track of is when did the longitudinal rebar in the column fracture? And that is what ended up happening. The concrete was well confined. We started getting fractures in the longitudinal bars in the columns. So we're figuring out, kind of when those fractures occurred, and that was what led to the strength degradation. So the long duration effect of the earthquake is having an effect there in creating that fatigue and causing the reinforcement to fracture. It is a fatigue fracture that's going on in the rebar. There's all 6 of the steel jacket tests. There's all 6 of the FRP jacket tests. So you see, pretty much good ductility in all cases. We actually didn't see as much difference among the test variables as we thought we might see. This is showing the deformation capacity in the columns. But one of the ones that I really wanted to highlight was when we did the FRP column, we did a column where we actually doubled the loading protocol. So we took our standard loading protocol and we applied twice as many cycles at each increment. Okay, so you see there, you can compare that. That's the same test as the first column. The only thing we changed was the loading protocol. So we really wanted to isolate that protocol and, just make sure that it was having the effect that we suspected that it might. And you see there that drop in deformation capacity when we hit it with even more cycles, right? But we're doubling something that was meant to represent the Cascadia Subduction Zone, full rupture. So not necessarily even a realistic protocol, but just an interesting data point to include. Now, one of the big concerns that we had, 3 minutes, okay. One of the big concerns that we had was rebar, right? Because the rebar, we're getting fatigue fractures in the reinforcement. The rebar that we used in our test columns had not been in the field for 60 years, right? So potentially a big difference there. So WashDOT sent us some rebar from demolished bridges, and we did some fatigue testing, some cyclic fatigue testing, set this up in our lab, and we found, sure enough, there's a big difference in the fatigue life of the rebar that we used in our columns versus what's out there in the field. So, recognizing that, we knew the deformation capacity was going to be a bit less in the real columns. So we took to modeling to kind of help us get through this. And we put together a model for the column where we can relate the deformation at the top of the column to what's going on down in the plastic hinge, where you're getting most of the action. So we set this up in OpenSees, which allowed us to use, OpenSees has very nice cyclic material properties that we could use for concrete and rebar. We could do a detailed fiber section analysis right down at the base where a lot of the action is. And as far as the zone of plasticity, that was another thing that was very sensitive in our model. How far is the plasticity spreading vertically in the column? And you get bond slip, you get strain penetration. So we looked at using an existing recommendation, which was 6 times the bar diameter for strain penetration. But in the end, we ended up deciding that that worked okay as you get out to the really big deformations. But at more modest levels, it didn't work quite as well. So we ended up modifying that, kind of checking a more refined bond slip model, and then using some tools that were available in OpenSees to model that bond slip down at the interface with the column and the footing. Effective stiffness, we used existing recommendations for effective stiffness of the column, and that included the jacketed region as well. We used an existing model to kind of deal with, the idea that you don't get full composite action right away. It takes a little time to develop that. So we used that existing model, and we also used existing models for fatigue. And when we put all of that together, we were able to get what we felt was a pretty good, pretty decent match between the model and the test. And our model allowed us to predict the bar fracture of at least the first bar. Beyond that, the model was not as accurate, but we were able to capture an estimate of the fracture when the first bar fractured. So you see that blue dot in the model, that was our estimate of first fracture. So not bad. The estimate for fracture tended to be a little on the conservative side, but from there the column, more bars in the column start to fracture and the column degrades. So run out of time, yeah. Okay, so I'll get through this quickly. The last thing we did here is kind of coming back to the original question and motivation for doing the research. We wanted to estimate how well these columns would perform in potential Cascadia Subduction Zone earthquakes. So we did a big parametric study here where we looked at different column cross-sections, and then we did a whole bunch of single degree of freedom nonlinear time history analyses. So we're changing the stiffness, mass, getting different periods, and looking at different, actually modeling, different columns in the single degree of freedom system. As far as ground motions, we used a suite of ground motions that were developed by University of Washington and USGS, which reflect predictions of they are predicted ground motions, simulations of a full rupture of the Cascadia Subduction Zone. So that's where the ground motions came from. We ran a whole bunch of analyses and used that to estimate the likelihood that we would see a bar fracture. So when I'm using the term failure here, this is a lateral load failure in the column, where you typically that's defined as a 20% loss of peak strength. So you're fracturing that first bar, you're starting to strength degrade in the column. Those are the predictions of fracture that we're showing here. By the time we would have a potential axial failure, you'd have to fracture virtually every bar in the column. That's what we were finding from the tests. So there's our kind of estimates of failure probabilities. Don't have enough space or time here to really show everything, but the trends were, as you got near the coast of Washington, you tended to see a spike in the shorter period structures. When you came out into longer period bridges, you tended to see a spike in the Seattle area, where you had the effect of the sedimentary basin actually amplifying the ground motion, the impact of the ground motion on the structure. So with that, I think I'm a few minutes over time. Sorry about that. So I'll throw the conclusions up and turn it over to you for any questions that you may have.
Thank you. Questions?
Oh, and I should make sure I thank all the sponsors that contributed to the research.